In this lecture, I would like to discuss about the chemical kinetic second experiment. In the chemical kinetic first, we has been discuss the reaction between potassium persulfate and potassium iodide, and we has been find out the order of the reaction and rate constant for that reaction. Now in this experiment, we are going to determine the energy of activation of acid catalyzed hydrolysis reaction of methyl acetate. The aim of the experiment is to determine the energy of activation of the acid catalyzed hydrolysis of reaction of methyl acetate. Hydrolysis of methyl acetate. Actually, hydrolysis reaction is a very slow reaction. Uh, Without catalyst, if the reaction is takes place, it requires a longer time. But in presence of hydrogen ions, the reaction takes place very fast. So you can see here the methyl acetate in presence of water undergoes hydrolysis, and hydrogen ion is used as a catalyst, and the product of the reaction is acetic acid and methanol. So particularly in this reaction, the hydrogen ion is used as a catalyst. So the function of the catalyst is to increase the rate of the reaction. The function of the catalyst is to increase the rate of the reaction. Now, what is the energy of activation? It is the minimum energy required for the reactants. Energy of activation, it is denoted by the letter EA. So energy of activation is the minimum energy required for the reactants to reach activated state. To reach the activated state. Suppose that A is a reactant and it goes to the activated state. And once it reaches to the activated state, then it is converted into the product. So this is called as the activated state. So to reach the reactant from the lower state to the activated state, the energy must be supplied. So in presence of the catalyst or in presence of the temperature, the reactant will be goes into the activated state. So let us see what is the experiment here. Now requirements. So to perform this experiment, we require 0.5 normal HCl. HCl is a catalyst here because it is acid catalyzed reaction. So we require 0.5 normal HCl solution. Then 0.1 normal NaOH solution. It is a burette solution. Methyl acetate, it is a reactant. Phenolphthalein indicator is required for the titration. Then glass stoppered bottles, 5 ml and 25 ml pipettes, conical flask, burette, ice. So these are the requirements for the experiment. Now let us see the set 1. In the set 1, we have to take the 100 cm cube of 0.5 normal HCl. We have to take 100 ml of 0.5 normal HCl in a clean glass stoppered bottle. It means in bottle number 1. And in the another bottle, we have to take 5 ml of methyl acetate in the another bottle. Or we have to fill the burette with methyl acetate. Then we can take the 5 ml of the methyl acetate. Now place both the bottles in water bath to attain the room temperature. We have to keep both the bottles in a water bath to attain the room temperature. So after some time, we have to withdraw that 2 bottles from the water bath. In the meantime, we have to fill the burette with 0.1 normal NaOH solution. Then In one bottle we have taken 0.5 normal HCl, and in another bottle we have taken 5 ml of the methyl acetate. Now we have to mix the methyl acetate into the 100 cm cube HCl, or with the help of the pipette we have to take 5 ml of the methyl acetate in bottle containing 0.5 normal 100 ml HCl, and we have to mix the reaction mixture. And after mixing the reaction mixture, immediately we have to withdraw the 5 ml of this reaction mixture in a conical flask. Once we add the methyl acetate into the HCl, then immediately we have to withdraw the 5 ml of reaction mixture in a conical flask containing few pieces of ice and 2 or 3 drops of 1% phenolphthalein indicator. Now we have to titrate this solution with 0.1 normal NaOH from the burette, and the end point is colorless to pink. So permanent pink color should be obtained there. So we should have to note this burette reading as a T0, because this is the reading at the 0 time. Okay, this is the reading at the 0 time. Now after 5 minutes from the 0 time, once again we have to withdraw, or we have to pipette out 5 ml of the same reaction mixture and transfer it into the conical flask containing the ice and phenolphthalein indicator. So in this way we have to take the second reading here, and we have to repeat the remaining readings as like of the first and second readings. It means we have to take the readings after 5-minute intervals. After 5 minutes interval, suppose we take the reading at 0 time, that is T0. Then after 5 minutes, after 10 minutes, after 15 minutes, 20 minutes, 25 minutes. So we have to take the 6 readings here. So as the time factor is goes on increasing, the amount of the reactant react is also goes on increasing, because as the reaction is takes place between methyl acetate, that is the hydrolysis reaction. So as the time factor is passes out, the more and more methyl acetate should reacts with water, and there is a formation of acetic acid and methanol. So formation of the product, it is goes on increasing, that is formation of the product acetic acid, or concentration of the acetic acid is goes on increasing. So it means that whatever the reading here, suppose it is 25.2, then the second reading it is around 26.0, third reading it is around 27.1. So in this way the burette readings are goes on increasing. The reason for to increase the burette reading is that as the time factor is goes on increasing, more and more reactant should be react, and there is a formation of product. So concentration of the product, that is acid, is goes on increasing. So we require more sodium hydroxide from the burette to neutralize that acid. That's why burette readings are also goes on increasing. Now let us perform the second set. Now second set, it is also as like of the set first. The process is same. Only the difference is that we have to perform the hydrolysis reaction at 10 degrees centigrade above the room temperature. The set first, it is performed at the room temperature. The set first, it is the reading we should have to take at the room temperature. Suppose that the room temperature it is 25 degrees centigrade, or in Kelvin it is 298 Kelvin. So at this temperature we have to take the 6 readings there for set 1. Now for the set 2 we have to increase the temperature by 10 degrees centigrade above the room temperature. Now if the room temperature it is 298 Kelvin, 298 plus 10, it is 308 Kelvin. So at 308 Kelvin, we have to do the hydrolysis of the methyl acetate. So temperature should be important here. The process is same as like of the set first. Once again, we have to take the 100 cm cube of the 0.5 normal HCl in the clean stoppered bottle, and we have to keep the bottle in a thermostat, maintain that at a temperature about 10 degrees centigrade above to that of the room temperature. Same can be process can be adapted in case of the methyl acetate. Okay, and after attaining this temperature, we have to mix the methyl acetate with HCl, and once again we have to take the reading at the 0 time. We should have to be note the time of mixing as a 0 time. Okay, and immediately we have to withdraw the 5 ml of the mixture to the conical flask containing few pieces of ice and phenolphthalein indicator. So in the second set, what is the difference is there? We increase the temperature. So as the temperature will be increases, the rate of the reaction will be increases. So comparative to the set first, set second readings are greater. So T0 reading here, suppose in case of the set first, it is 25.2. Now in case of the set second, the first reading, it is around 26.0. Okay, so there is an increase in the burette reading because as the temperature is goes on increasing, the rate of the reaction should be increases. So more and more product is formed there. So speed of the reaction is increases there. Okay, so the process of the set 2, it is same to that of the set 1. Only the difference is that we have to increase the temperature by 10 degrees centigrade as compared to the set 1. So in this case also we have to take the 6 readings, reading at 0 time, then after 5 minutes, 10 minutes, 20 minutes, 25 minutes, like that. So 6 readings we have to note it. Okay. So this is the observation table here. So at room temperature, suppose it is 298 Kelvin, then T infinity. So to take the T infinity means the burette reading at infinite times. The burette reading at infinite times. So generally after 48 hours, okay, after 48 hours we have to take the readings. We have to keep that bottle of the set 1 for 48 hours, and after 48 hours we have to note that reading. So that T infinity reading should be around 50 cm cube because the reaction is completed. T infinity, it is the time at which the reaction between the methyl acetate and water is completed. So that's why it is called as a T infinity. So on the basis of this T infinity, we can determine the initial concentration A, that is T infinity minus T0. T0, it is the reading at the 0 time, and T infinity, it is the reading at the infinite times. So according to this, we can determine the A here, concentration of the initial concentration of the reactant. What is A here? A, it is called as initial concentration of the reactant. Initial concentration of the reactant. So on the basis of this, we can find out the initial concentration of the reactant. So this is the observation table here. Okay, this is T0, it is the reading at the 0 time. Okay, so these are the titration readings. Then X, it is the amount of the reactant reacted at the time T. So it is Tt minus T0. A minus X, so we know this A initial concentration minus X. So we should have to be right here T infinity minus Tt, it is, and X, it is Tt minus T0. So if we take the readings here, then we have to fill this table by doing the calculation. And the last column, it is K1, it is equal to 2.303 upon T log of A upon A minus X. So we have to determine the rate constant here, K1. We have to determine the rate constant K1. Okay, where A is the initial concentration, X is the amount of the reactant reacted at the time T, and T is the time. And K1, it is called as a rate constant. So this equation, it is the first order kinetics. It means that the reaction between methyl acetate, and water, it is a first order reaction. It is a first order reaction. The rate of the reaction is depends upon the concentration of this methyl acetate. The rate of the reaction, it is depends upon the concentration of the methyl acetate. Of course, the molecularity, it is 2 here. This is one molecule, this is one molecule. So molecularity is 2, but the rate of the reaction does not depends upon this. The rate of the reaction, it is depends upon the concentration of the methyl acetate. So this is the rate equation here. So we have to do the calculation. 6 calculations are there. Okay, and take the mean K1 value. Similarly, the observation table for the set 2, it is as like of this, and we have to determine the K2 at temperature T2. Here K1 at temperature T1. K1 at temperature T1, and this is for set 1, and K2 rate constant at temperature T2. This is for the set 2. So observation table for the set 2, it is also same. Okay, so T2 it is T1 plus 10. So these are the equations are given to calculate the rate constant. So K it is equal to 2.303 upon T log of A upon A minus X. So we already discussed this. So K it is equal to 2.303 upon T log A minus log of A minus X. So log of A minus X, it is equal to, so this is log A, it is equal to KT upon 2.303. So we have to plot here the graph of log of A minus X against the time T for both sets, and the value of the K, it is also obtained from the two graphs. Okay, the rate constant K, it is obtained from the two graphs. Okay, so this is the nature of the graph. You can see here log of A minus X versus time T. So it is descending but straight line, intercept onto the y-axis. So slope it is equal to AB upon BC. Here we can determine the slope, or y2 minus y1 divided by x2 minus x1. So we are getting here the slope value, and on the basis of the slope we can determine the rate constant. Okay, so the rate constant, it is equal to, the rate constant, it is equal to slope multiplied by 2.303. Suppose K1 it is the rate constant for the set 1, so it is equal to 2.303 multiplied by slope here. So by using this we can determine the rate constant for the set 1. Similarly, K2 it is equal to 2.303 multiplied by the slope of the second set. So you can see here K1 at temperature, the two temperatures are given here. So generally the value of the K2 will be higher than K1, because for the set 2 the temperature is higher. So the K2 value, rate constant value, it is also higher. Okay, so you can hear specific reaction rate or rate constant by calculation and by graph. So we have to find out the rate constant K by calculation as well as by graph. And once we determine the K1 and K2, then we can determine the energy of activation, because the aim of the experiment is to determine the energy of activation of hydrolysis of methyl acetate, acid catalyzed hydrolysis of methyl acetate. So with the help of this formula, or with the help of this equation, we can determine the energy of activation. Okay, so EA, energy of activation, 2.303 log to the base 10 K2 upon K1 into R, T1 T2 divided by T2 minus T1, where EA, it is called as the energy of the activation for the acid catalyzed hydrolysis of methyl acetate. Okay, so we have to put K1 and K2 value here, T1 and T2 value here, and we are getting the this energy of activation. So we have to represent the results in the tabular form. So K1 at room temperature. So we have to write that calculated value here. The rate constant has the unit per minute. Okay. Similarly K2, and final it is energy of activation. So in this way, in this experiment, we can determine the energy of activation, to determine the energy of activation of acid catalyzed hydrolysis of methyl acetate. So thus we have to perform this experiment in the two set. We have to perform the experiment in the two set. In set first, the room temperature can be noted, and at the room temperature we have to take the readings. And in the set second, we have to increase the temperature by 10 degrees centigrade. So as the temperature will be increases, the rate of the reaction is increases. So comparatively, the rate constant for the set K2 will be higher than the rate constant of the set first. So K2 it is higher here as compared to K1.